Welcome to the 2016 AP Statistics FRQ exam. In this video, we're going to feature question number 2, all answers and solutions fully explained. It was a really good chi-squared question that a lot of kids aren't great at because they kind of learn it towards the end of the year, but hopefully I'll do a decent job explaining it and you'll be able to ace it. But before we get too far, don't forget to like and subscribe and hit that notification bell as well for me. Thank you, I'd appreciate it. All right, looking at question number 2, product advertisers studied the effects of television ads on children's choices for 2 new snacks. The advertisers used 2 30-second television ads in an experiment. One ad was for a new sugary snack called Cocoa Zooties, and the other ad was for a new healthy snack called Apple Zooties. For the experiment, 75 children were randomly assigned to one of 3 groups, A, B, or C. Each child individually watched a 30-minute television program that was interrupted for 5 minutes of advertising. The advertising was the same for each group with the following exceptions. The advertising for Group A included the Cocoa Zooties ad, but not the Apple Zooties ad. The advertising for Group B included the Apple Zooties ad, but not the Choco Zooties ad. And the advertising for Group C included neither the Cocoa Zooties or the Choco Zooties, however you want to say that, nor the Apple Zooties ad. So Group A had the Cocoa Zooties ad, Group B, Apple Zooties ad, Group C, neither. After the program, the children were offered a choice between the 2 snacks, and the table below summarizes their choices. So they're trying to set up a really good experiment here where everything is kept the same 30-minute television program, interrupted by 5 minutes of advertising. The only difference between these 3 groups was there a 30-second ad for Cocoa Zooties, a 30-second ad for Apple Zooties, or no ad for those. And then they wanted to see, after the kids watched the program, what choice they would make. So in Group A, where they only watched the Cocoa Zooties ad, 21 kids chose Cocoa Zooties, 4 chose Apple Zooties. In the Group B, only watching the Apple Zooties, 13 kids chose the Cocoa Zooties, 12 chose the Apple Zooties. And in the Group C, where neither ad was showed, 22 kids chose the Cocoa Zooties and only 3 chose the Apple Zooties. All right, so let's dive into what the question is. Question A, there's 2 parts here. Question A says, do the data provide convincing statistical evidence that there is an association between the type of ad and children's choice of snack among all children similar to those who participated in the experiment? So if you understand what's going on here, the first thing I notice in that table is I notice counts of kids in each category. Anytime you're dealing with counts, you're more than likely looking at a chi-squared test. And on top of that, we see more than one count. If we only had one count, like we were just looking at the proportion of kids that chose Apple Zooties and that was it, then we could probably do a Z test here, a 1 sample Z test. But the fact that we got multiple groups, not just 1 or 2, we got multiple, in fact we got 3, that's instant sign that we're going to be needing a chi-squared test here. Chi-squared is going to be for counted data when there's definitely more than 1 to 2. So here we got 3. So to check for convincing evidence, I am going to need a chi-squared test for homogeneity. Now, why is this homogeneity? Well, because I have one group of kids and I separate them into groups, and each group did something different. That's the idea of homogeneity, right? Homogeneity means that we went in expecting, our expectation, our null hypothesis should be that they're all the same. It doesn't even matter what you watch, right? They should all be the same between the different groups. And the alternative is that there's going to be a difference between what happened in each group. Now, this is not an independence test, because an independence test is when you have one group of people that you measured them twice, like you looked at their gender and their political party affiliation, and you want to see if there's an association between those 2 things. But again, you had one group of people, you just asked them 2 questions. We don't have that going on here. We have 3 completely separate groups of people. All right, this is also not a goodness of fit test, because we were looking at multiple categories across our different groups. We were looking at, did you choose Apple Zooties or did you choose Cocoa Zooties across the different advertisements, A, B, or C. So goodness of fit test is when there's only one categorical variable. We have definitely 2 categorical variables here. What advertisement did you watch and what did you choose? And again, it's homogeneity because we have one sample, originally 75 kids, but we broke them into different groups, and each group did something different. It wasn't just one group measured twice. So I want to make sure I'm clear on the breakdown between those different types of chi-squared tests. All right, now to actually conduct a chi-squared test, there's 4 steps. Name and give the hypotheses, check the conditions and find the expected values, get the chi-squared total and the p-value, and then create your conclusion. So I'm going to walk through those 4 steps with you right now. So step 1, this is, again, as I already mentioned, I actually wrote that wrong. I'm going to change that right now. I can't believe I had that typed wrong. A chi-squared test for homogeneity. I think when I was originally planning this, I originally jumped to the conclusion that it was the independence, but I fixed it in one spot, not in the other. So I apologize for that. So this is the chi-squared test for homogeneity between type of ad and children's choice of snack amongst all children, similar to those in the study. The null hypothesis would be that the proportion of children who would choose each snack is the same regardless of which ad they viewed. So your null hypothesis is always that there's no association, there's no connection, everything is the same. So whether you watched A, B, C advertisement, doesn't matter. The same proportion of kids chose Apple Zooties as Choco Zooties, doesn't matter. The alternative hypothesis is the proportion of children who chose each snack differs based on which ad they viewed. So the alternative is no, that this is maybe what they're trying to show is that the ad you watch does impact what snack you choose. So the proportion of children who would choose each snack differs based on which ad they viewed. All right, so now I'm going to go ahead and get my conditions. So the first condition is that we have to have that idea of randomness. We do have randomness here because the 75 kids were selected, and then which kid went into each group was randomly selected. So we do have that layer of randomness here to remain unbiased. Now the next condition is that the expected counts in each cell have to be 5 or greater. So I need to get my expected values to prove that. Now here is how I did that. So in this table, the first thing you're going to realize is I have, and it's actually nice when you actually have a chi-square test. I highly recommend creating a little table just like this. So first I have the original values. That's the 21, 13, 22, and then the 4, 12, and 3. If you could go back to the original table to see that. In parentheses, I have the expected values, but let me walk you through how I got those. So first, I had to think everything's the same, right? So I had to look at my totals. Now, it's not about being 50-50. It's about the totals being the same. So I said, okay, I got 56 total kids that chose Choco Zooties, 56 divided by 75. That proportion is what I should see amongst each group of 25. 56 out of 75 should be the same across the groups. And that ended up working out to be 18.67. 56 out of 75 is right about 75%. So again, we should see 75% of each group choosing Choco Zooties. 19 out of 75 is just about 25%. So we should see 25% of each group choosing the Apple Zooties. So that's how I got the 18.67. That is 75% of 25. And that's 6.33. That's about 25% of 25. Now, another way you could also get your expected values is to take, for example, in this value right here, in this group, Group A, Choco Zooties, take your row total, 25, times your column total, 56, divided by 75, your grand total. So row total times column total divided by grand total. And if you do that for each one of these cells, you will get the 18.67 for these 3 on the left and the 6.33 for the 3 on the right. Now again, I needed to check my expected values because that second condition is that the expected counts all have to be 5 or more, and the 18.67 and 6.33 are all 5 or more, so we check that out. Some kids accidentally think that the observes have to be 5 or more, and they'll think, oh no, I only have 3 observes right here, that's a problem. No, that's not a problem at all. It's the expecteds that have to be 5 or more. So again, if the proportions are all the same, again, notice the proportion, not the number of, the proportion have to be the same. That's where we notice again that 56 out of 75 is about 75%. That's what I have to see the same for Choco Zooties, and the 19 out of 75 to 25%, that's what has to be the same for Apple Zooties. All right, now to actually calculate my chi-squared and my p-value. So the formula for chi-squared, it is on your formula sheet. I hope you know it. There's my little chi-squared symbol. Looks like an x squared, but it's the Greek letter chi. It's the observed minus expected squared divided by expected for every single cell. So in the first cell right here, I did the observed 21 minus 18.67 squared divided by the 18.67. Then I did the same thing here, 13 minus 18.67 squared divided by 18.67, and same thing here. And then I just repeated that process for the apple zooties. 4 minus 6.33 squared divided by 6.33, 12, and then 3, repeating that process over and over again. Now, I accidentally have equal signs here. I apologize. Those should all be plus signs because that's what this little summation symbol means. We're going to add all of those together. So we're adding up our grand total of our chi-squared. So I've calculated each of those chi-squareds individually using my calculator. Got 0.291, 1.722, 0.594, 0.858, 5.079, 1.752. Added them all together to get my grand total chi-squared. Now, just a couple comments on rounding. Very minimum 2 decimal places. I actually prefer 3. For the expected values, I did go with 2, the 18.67 to 6.33. Maybe could have a little bit better if I kept an extra decimal point. Not the end of the world. But then for my chi-squareds, I went with 3. Again, you could probably get away with 2 decimal places, but I'm trying to be as accurate as possible, so I went with 3 decimal places when I added them all together. Now, to get your p-value, the p-value is the probability of that test statistic chi-squared being greater than 10.296. Chi-squareds can only be positive, obviously because of your squaring, so that you're always looking greater than your chi-squared value. On a TID4 calculator, you're going to be using your chi-squared CDF. And when you go to chi-squared CDF, your upper value is going to be that 10.296. Your upper value is going to be 999, just going all the way up to infinity, essentially. Now, we got to talk about degrees of freedom. All right, across the rows here, we have 3 rows. 3 minus 1 is 2. And then across the top, we have 2 columns. 2 minus 1 is 1. So you take that 2 times the 1 to get 2 degrees of freedom. Again, it's categories and their rows minus 1. 3 categories minus 1 is 2. Categories in your columns, 2 minus 1 is 1. Multiply those together, 2 times 1 is 2, so 2 degrees of freedom. And the p-value I got was 0.00581. Now, what does that p-value tell me? It means that the probability of seeing these observed values, when I was supposed to see these expected values, the probability of this happening is 0.00581. Now, that's pretty low. That is under 1%. That's under 5%. That means that my observed values should not have occurred if the expectation was that the proportions are the same. So that means that we are going to reject the null here. There is statistical evidence to say that the advertisements did have an impact on which snack the kids choose. So here I am saying that. Since my p-value of 0.00581 is less than 0.05 or even 0.01, this is an important part of a conclusion. A lot of kids forget about it, but you do have to have a comparison to your alpha. And then I'm going to reject the null. So that's kind of the second point that you need to have is, what are you doing because of your p-value? I'm going to reject the null. And the third thing is the context. So there is convincing evidence that the proportion of all children similar to those in the study that select each snack does differ based on what ad they watched. Don't have to get too much into specifics here about, what ad caused what change, but just as generic, you're basically agreeing with the alternative hypothesis here is that the proportion of children who select each snack does differ based on the ad they watched. So again, hopefully that all makes sense. If we go back to the data, we could kind of see, we kind of eyeball which ones kind of have the biggest changes here. The biggest change is probably this one right here. So in group B, where they watched the Apple Zooties ad, we ended up getting more kids choose Apple Zooties than we originally would have thought. So hopefully that makes kind of sense there. Now, there was a follow-up question to this. It says, write a few sentences describing the effect of each ad on children's choice of snack, which is kind of what I was just alluding to a moment ago. So the first thing I said was when neither ad was viewed, way more children chose the Cocoa Zooties, 88%. So again, when no ad was viewed, that's why I went back up here, that's 22 out of 25, 88%, C was neither ad, 88%, 22 out of 25, kids chose the Cocoa Zooties. Now, when only the Cocoa Zooties ad was viewed, it was not a major change, it was 84%. So it's kind of interesting that if there was no ad, more kids chose Cocoa Zooties, but when there was an ad, a little bit less. But again, it wasn't majorly less. 88 to 84 isn't a major change, especially when you're dealing with small samples of only 25 kids. But here's where we saw the biggest effect was Group B. This was the Apple Zooties ad only. After being in Group B, we saw a significant decrease in the amount of kids that chose Cocoa Zooties. Only 52% chose the Cocoa Zooties. The remaining 48% chose the Apple Zooties. So it does seem that seeing the ad for a healthier snack did relate to the kids and made you connect with them more, and it caused them to be less likely to pick that sugary snack, the Cocoa Zooties, and go with the Apple snack. Now again, at the end of the day, even with that Apple Zooties ad, 52% of kids still picked Cocoa Zooties. But again, when no ad was viewed or when the Cocoa Zooties ad was viewed, it was up in the 80%. So we did see a significant drop when they had an ad for a healthy snack. So hopefully that's good news, that if kids are showed more ads for healthy snacks, they will choose those healthy snacks. But a great problem here to see all of this. Hopefully it wasn't too bad for you. Chi-squareds do tend to be a little bit of work because doing all the math work here for the chi-squared test does take some time. But overall, it's a pretty simple problem. It's not overly difficult when you understand how to do it, obviously. It's not too bad. But keep in mind that idea that why this is a homogeneity test, because we had 3 separate groups, each group doing something different, as opposed to a test of independence where we have one group measured twice. Like again, the example of gender versus political party affiliation, something like that. So hopefully this made sense. Don't forget to like and subscribe, and I'll see you in the next video.